This question's to check your understanding of states of matter and your ability to represent them at the molecular level. So we have 3 states of matter that I want you to show: solid, liquid, and gas. If you want to reference anything, you can look back at your notes that we took at the beginning of the year. This sheet has some notes on it that we're going to use for this. And so visually, these are the solids, liquids, and gas models that I want you to use. So a solid, it's asking you in this question to use 9 atoms, and the atoms are these solid dots. So in a solid, you want to show that you understand that a solid is structured, has a regular structure to it. A crystal of this, they would be stuck to each other. Their attractions in a solid are the highest, and that's why they're a solid at room temperature. Now, one of the misconceptions about a solid is that it's not moving at room temperature. I'd like you to have a model in your head of the atoms being stuck to each other and wiggling. Now, in this right here, this example, they are stuck to each other and they're able to wiggle, but they're not moving around each other. So this is a good simulation for what water would look like as a solid. As a liquid, you're going to show them all touching again, but this time they can now move around each other, and they're not going to be as organized. So I'm showing them right next to each other. You don't want to show them spaced out. One of the misconceptions people have is that in a liquid they get quite a bit further apart from each other. In a liquid, they're still pretty much right next to each other, but they're able to move around. So again, I'm only using 9 dots to represent this. It's not a regular shape anymore. It takes on the shape of the container. And so when we add energy to water, eventually it gets enough energy that it doesn't have that regular structure anymore. These water molecules are now free to move around and around each other, but almost all of them are still stuck to each other. So this represents a liquid for the most part, with a few molecules that have moved away into the gas state. Then representing a gas, that's when each one of these atoms gets enough energy to be able to separate from the other atoms, and they spread out. Now, this is the point when they're moving the fastest. And the model I want you to have is when they have enough energy that they can break apart and they are able to get away from the water molecules next to them. So as I add more energy to these water molecules, they're able to overcome the attraction between the water molecules. Some water molecules might stay stuck to each other for a little bit of time, but eventually they bounce around and move away from each other. As I add more and more energy to this, then they're less likely to be stuck to each other. So down here, it's asking about the relative attraction between molecules in a solid liquid. If they were all at room temperature, it couldn't be the same substance. So 3 examples that you might have are a rock, water, and air. Now, rock and water are compounds, and air is molecules, a mixture of molecules, but a rock is a solid at room temperature because the attraction between molecules is so great. It's a solid that has the highest attraction between molecules compared to the liquid and the gas. Water has a high attraction, but not so high that it fixes all the molecules in place. So it has a high attraction, but not the highest attraction when you're comparing solid, liquid, and gas. A gas has a very low attraction between molecules, and that's why they're able to separate at room temperature.